Howdy! We are the 12th Astronaut Lab from Texas A&M University. Our project this semester is designing an augmented reality visor for future Artemis astronauts. My name is Israel Gomez, and here are the team leads, most who will be presenting today. NASA Suits is a project hosted by NASA and given to colleges and universities around the U.S. to help future Artemis astronauts during the Artemis mission. The four main goals of NASA Suits are to create an augmented reality visor that improves the speed and accuracy of lunar navigation, to create an interactive EVA system state, to aid in future geology sampling, and to consider any auxiliary considerations.
The Texas Space Grant Consortium is a student design project geared towards letting students solve problems and collaborate with NASA researchers to address challenges faced by NASA. The 12th Astronaut Lab had two teams compete this year. The first is the 12th Astronaut team, working on the NASA Suits Design Challenge. The second is the 12th Eclipse team, working on producing an augmented reality HoloLens application to provide astronauts with assistance for task completion on the ISS. Both of our teams presented at the 2020 TSGC Virtual Design Showcase this fall and received recognition by the judging panel for our various designs.
As a team, there were three main problems we decided to tackle. The main issues being 1. A lack of astronaut independence on EVAs, especially regarding specific tasks and missions. 2. Limited communications with mission control. And 3. Inefficient time for IVA task completion, as well as storage inventory and access.
EVAs, or extravehicular activities, are directed by the IV members, or the intravehicular crew members, who read out the steps to the EVA crew and help to direct them through it. IVA members and the MCC can monitor the EVA crew's progress and communicate with them, but there is no visual monitoring of the EVA crew members for the MCC, which can be a detriment during EVAs.
Astronauts living and working on the International Space Station complete many different tasks, including experiments, exercise, and other various activities. To prepare for these tasks, astronauts train for years on the ground to familiarize themselves with the procedures. Once on the ISS, astronauts use computers on board along with their iPads to receive information regarding tasks that they need to perform from Mission Control Center. Our team is designing augmented reality panels to reduce the time spent referring to iPads and allow real-time dynamic assistance with IVA procedures.
To tackle the problem of creating an AR visor design for astronauts, we've come up with an AR assistant that helps remote users interact with astronauts in the field. The device's name is Scout, and it stands for Space, Communications, Operations, and User Telepresence. We named it after one of our coworkers' pets.
This block diagram starts with a remote user in a VR headset, seen in the blue block on the left. This remote user may either be someone in mission control or another astronaut located in a nearby habitat. This remote user has the ability to spawn holograms to help with navigation, geology sampling, and other mission tasks that may occur. We've implemented this design on the HoloLens 2, which has the capability to make a real-time 3D scan of the environment around the astronaut. This allows the remote user to have complete situational awareness without the need for a high-bandwidth video stream. These features are achieved through a remote client device and local computational server that processes all of the data as needed. Our user interface features a series of floating menus that can be seen in the picture on the top right. These menus are overlaid on top of the environment within the astronaut's visor, and in this case, may display holograms such as 3D waypoints and splines to help with navigational tasks. The menus can also follow the user or stay still, and also have a customizable level of transparency. The 3D TELEPRESENCE whiteboard is a new feature we've developed that allows mission control to remotely guide astronauts during EVA surface operations using splines and holograms in 3D space. Instead of having to solely rely on an audio loop for task assistance, such as in the past, the EVA crew member will now have customized visual cues floating in front of them. This technology helps guide the astronaut through each task using any drawing that a crew member or a mission controller may create.
To help with the design of these features, the research team has been assisting the technical team members by conducting any background research that they've needed over the course of the semester. Some of these topics have been the hand gesture capabilities of the HoloLens 2, the difference between voice command capabilities of the HoloLens 1 and 2, and different note-taking options that could be implemented into the geological sampling portion of the NASA Suits Challenge. We have also conducted a study testing the efficacy of the whiteboard telepresence and plan to publish this study in the Virtual Reality Journal. We are also still working with the technical team to conduct a research study testing our final design to see if there are any trouble spots remaining.
The finance team has been helping our team generate funds for our operations, and we've generated a portfolio of products, and we're currently working on distributing those products. Well, in addition, we're working on the TSGC grants and other profit shares and grants.
The following are video demonstrations of the augmented reality user interface and telepresence whiteboard in both EVA and IVA settings. This video shows the simulated experiment of growing protein crystals on the ISS. The procedure being followed is to take the protein solution from the first Petri dish and add it to the protein molecules in the second Petri dish. Finally, place the crystals under the microscope to check that they have fully formed. The astronaut is shown using the multiple panel display settings and location options to customize the information shown in a way conducive to the experiment. The full detail view and diagram view are beneficial as explanations of the procedure, while the current step view is less obtrusive and easy to display while completing the experiment. These panels will save time spent referring back to procedures and will give astronauts a more interactive and efficient method of completing experiments. This design will also increase the ability to communicate with the experiment designers on Earth.
This video showcases the 3D telepresence whiteboard used in a simulation on the lunar surface. The primary tool for remote annotation is the spline pen, which is currently drawing green splines. The remote user may freehand draw in any shape. There's also functionality to undo, redo drawings, and options to change drawing color and size. In this case, it is pointing out a rover display panel within the simulation. Lastly, the astronaut's visor in the field sends back crew member transform data as well as scanned environment mesh data. This makes sure that mission control will have situational awareness of the area surrounding the astronaut at all times.
Some of the ways we've achieved these goals was through a publication of our study and a paper submitted to the IEEE conference. Our study found that the whiteboard telepresence design that we created decreased task completion time by over 60%. We also developed a real-time AR assistant, Scout, which helped create efficacy in navigation, geology sampling, and was able to show the suit state and mission operation parameters. For some acknowledgements, we would like to thank our advisors, Dr. Gregory Chamitoff and Dr. Anna Diaz-Artiaz, and our supporters from NASA Suits Competition, the TSG Design Challenge, and the Texas A&M University Engineering Department. We also like to thank our fellow students, professors, and our former members. As a final thing, here's a picture from our team before COVID hit and gig 'em.